Okay, now if you recall from last time, there were 5 steps. And doing a hypothesis test or testing a claim about a population mean or a population proportion involves going through these 5 steps. And so what we just did on that worksheet were steps 1 and 2. So step 1 is to always write the hypotheses. In every test that we do, from now until the end of the semester, there will always be 2. These 2 hypotheses will be competing hypotheses, which means that only one can be true at a time. If we reject the null hypothesis, then it must mean the alternative hypothesis is what we have evidence for. If we fail to reject the null hypothesis, then we don't have evidence to support the alternative. But there are only 2. They are competing, and we're going to write them usually with our mathematical language. We're going to convert the words into a symbol and a number with an inequality symbol. The next thing would be to identify the level of significance. And so this is the alpha value that you also did that. A lot of times, this is going to be the easiest step because they give you this right in the problem. And you just write it down, alpha 0.05, or some other level of significance. Now, I also shared with you last time how to write the conclusion. So the conclusion is step number 5. This is the concluding statement that you write that kind of summarizes what you found in the hypothesis test. And you're going to say something like, there's evidence to support the claim that, or there's not enough evidence to support the claim that, and you write out what the claim is. So I gave you a template last time on how you would actually write that conclusion. So we've already done that one. The 2 middle steps are what we're going to focus on today, 3 and 4. 4 is going to be based on all of the work that you do in step 3. And what you do in step 3 is to gather all the evidence that you need to make the decision. And then step 4 is to make the decision. But step 4 always follows from the evidence that you found in step 3. And this is going to be a multiple choice. And you're either going to say the evidence from number 3 requires that we reject the null hypothesis, or the evidence from step 3 suggests that we should not reject the null hypothesis. And you're going to do just one of them. You're just going to select one. The decision is to reject the null hypothesis. Why? Here's why. And then you write the conclusion. So step 3 is the longest step, and this is where you do all of the numerical calculations that you need to do that will enable you to make the decision. And a couple of the numbers that well, there are 2 methods, all right, maybe 3, but we're going to focus on just 2 in our first couple of problems. The third method involves using a confidence interval. So we'll talk and see how confidence intervals are related to, or can be used to make the decision in a hypothesis test. There's the classical, all right. So you know what classical means, classic Coke and so on. It's the old version, the version we used to use a long time ago. And then there's the p-value approach. Now the p-value is a probability that we've calculated many times in earlier chapters. It's the same p-value. Usually, after I show you once or twice how to get it and how it relates to what we've done in the past, we'll just use the technology to crunch that number for us. So what I'd like to show you today is this classical approach and the p-value approach. The middle steps. And then we'll put it all together and do a couple of problems from start to finish, doing all 5 steps and then some. All right, so you have a couple of pages of notes from section 10.2. These are in the e-learning. And the first approach is the classical approach. And this is the approach where we draw a sampling distribution, you know, one of those bell-shaped curve, and we shade it and we label it, and then we go calculate a test statistic to see where the test statistic falls on our graph. Last time we looked at the 3 different kinds of tests. Two-tailed test, and remember the two-tailed test is marked by the inequality sign. In the alternative hypothesis. So when you have a not equal to, in the classical approach, you're going to have area on both the left and the right side of your bell-shaped distribution. It's going to look like this. For a two-tailed, you're going to have area over here and area over here. In a left-tailed test, you see the less than sign there. In a left-tailed test, the less than sign will always appear in the alternative hypothesis. And when you do the sampling distribution for a left-tailed test, the area will appear to the left. And finally, for a right-tailed test, you can identify a right-tailed test because the alternative hypothesis will have a greater than sign. And some of your problems in the homework will be, is this a left-tailed test, right-tailed test, or two-tailed test from section 10.1? And you look at it right here. A couple of other things you should be aware of is that, you know, whatever this number is that appears in the null hypothesis, the claim, remember we're going to assume that the claim is true, this P0, it's a number. You saw in some of your examples what that number might be. So I think in one of them, you had P equals 0.61. So you're actually going to put a number in here and not the P0, but the P0 can represent the number that corresponds to the claim. And then P is not equal to 0.61. So the P0 in all of these will be replaced with a number once you get a specific problem. Right now, they're just saying in general, P0. Now that P0, that's part of the claim, you're going to put it in here and calculate NP0, Q0. And remember, in order to use a normal sampling distribution, that product has to be larger than 10. So based on what we know about the sampling distribution, we're going to assume the claim is true, and we're going to draw one of these pictures right here. Two-tailed test, one-tailed left, one-tailed right. The other thing is that if alpha is equal to 0.05, when you draw these pictures to try to find these critical values, and we're going to use the same thing we used before to find those critical values, the inverse norm function, that's going to establish the region where we do not reject the null hypothesis and the region or regions where we do reject the null hypothesis. When you have a one-tailed test like this one and like this one, and you've established alpha to be 0.05, then all of the 0.05 goes in the one tail. If alpha is established to be 0.05 and you have a two-tailed test, then you want to split that 5%, that 0.05, and put half in one tail and half in the other tail. Alpha has to do with, you know, the most extreme 5% of the samples. In a one-tailed right test, the most extreme 5% of the samples would appear to the right. In a one-tailed left test, the most extreme 5% of the samples would fall to the left. But in a two-tailed test, most extreme 5%, since we are going to allow the sample mean to be on the left or the right, we divide that 5% up into half. And then the percentages that we have for the area and the tail will help us identify the critical value. So let me just add a little bit more detail to this picture here. If you have the mean is, now let me go ahead and do P equals 0.61 and P is less than 0.61. And this was the claim. I think this was the claim in one of our problems that we did. All right, now this number right here is the P0. The number that appears in that null hypothesis is part of the, was it 0.61 or, well, there was one that was 0.61 and one that was 0.62. So I think the one with, well, we'll just go with it this way. So we really should check P0, Q0 times M, and we need to get something larger than 10. So in the problem, you know, they'll give you a sample size. I don't know what it is here. Let's say it's 300 in a problem. But what this number is here, P is equal to 0.61. This is what we're going to assume the sampling distribution looks like. So we're going to put the 0.61 right here, right in the middle. Now on the Z distribution, that corresponds to a 0. You can see that we're in a Z distribution because if you take 300 times 0.61 times 0.39, and remember 0.39 is 1 minus 0.61, you get a product that's larger than 10. You can confirm that pretty quickly. All right, so all that tells us is that we have a normal sampling distribution. All right, so because of the less than, and let's say that alpha is equal to 0.05 here, double of significance, we're going to put the entire 0.05 in the right table. Oops. Less than. Doesn't go over there. It goes over here. Less than. Look at that one. Now, if we know that this is an area equal to 0.05, because that's what alpha is, then we can find this number here. We're in a Z distribution, so that number is inverse norm of 0.05. Now, I'm not going to use the mean and the standard deviation of the sampling distribution. I'm just going to use the Z distribution because this is what we use when we're using the classical approach. And I believe this number is negative 1.645. And this is what we're calling Z of alpha. It's actually the negative Z of alpha because it's the negative one. I rounded it a little bit. All right, so here's how we're going to label this. Now, if we get a sample proportion close to 0.61 in this range, we're going to just attribute that to random sampling variation. We take one sample and we would get this sample proportion. It's close to 0.61. If we did another one, we might get this one. And we would just generate all of these p hats. Every time we took a new sample, we'd get a different sample proportion. There'd even be some, you know, way over here and some way over here. But we know that most of them will fall in the middle if the population proportion really is 0.61. So here's what we're going to do. If we find a sample proportion that puts us in this range, we're going to say there's not enough evidence to reject the null hypothesis. Any number that we find over here from this point over, this is our line in the sand right here. So we're going to define what we do if we find a sample proportion to the right, and what do we do if we find a sample proportion to the left. If we happen to find a sample proportion that's a long way away from 0.61, like 0.43 or something way over here, then this is going to lead us to reject the null hypothesis. And the null hypothesis is that the population proportion is 0.61. So we would reject that if we got a number over here. So I just wanted to add to this picture this and this, because this tells us whether or not we reject the null hypothesis. Now, what are we going to do from here? We're going to calculate a test statistic. Our author describes that as Z sub 0 because it corresponds to the sample proportion that we get in the problem. So let's say that we took the sample and we found the sample to be 0.59, the sample proportion. Now you'll notice that in comparison to the claim that the proportion is less than 0.61, 0.59 is in fact less than 0.61. So the question is it less enough to cross this line in the sand that would enable us to say it's significantly less than 0.61, and that would lead us to reject the claim that the population proportion is in fact 0.61. So we use this sample proportion, come on down here, and the test statistic that we're going to use, this is in section 10.2 for sample proportion, is we're going to take the sample proportion, subtract what we think the population or what the claim thinks the population proportion is, and then we're going to divide by the, we call the standard error term. And that is P0 times Q0 over to N. All right, so this is a test statistic. So we're going to plot this test statistic and see where it falls. If it falls over here, we're going to reject the null hypothesis. And if that test statistic falls in here, over to the right of this line, then we're going to fail to reject the null hypothesis. And that's the classical approach. So we're not going to say that a number, a sample proportion less than 0.61 is necessarily going to give us evidence to support the claim that the population proportion is 0.61. It has to be significantly less than 0.61. So the question is 0.59 significantly less than 0.61? And that's where this comes in. Okay, the p-value approach is the other approach. And the p-value is the probability, assuming the null hypothesis is true, that we would find our sample statistic or something more extreme. Now, what it means to be more extreme would be further away from the middle. So, all right, so let me draw this picture again. So I can give you the p-value. Here was the 0.61. And then over here somewhere, we found the p-hat to be 0.59. So this is the p0 that appears in the null hypothesis. And here is the 0.59. Now, I purposely didn't draw the line in the sand here, but we do know that the alternative hypothesis is that p is less than 0.61, and that is our claim. Now, since we have a less than over here in our alternative hypothesis, and we know that this is a left-tailed test, that to calculate the p-value, it's the probability of getting our sample proportion or something more extreme. And since the alternative hypothesis, we're interested in proportions that are less than 0.61, being more extreme would be equal to what we observe, 0.59, or something more extreme over here. So this area here is the p-value. The probability of getting our sample proportion or something more extreme or something less. So the p-value in this case is the probability of getting a p-hat that is equal to our p-hat, 0.59, or something less. And we can calculate this because it's in a normal distribution. It's normal, CDF. And we go negative infinity, so negative 10,000 to 0.59. That's the region here. And then we would have to enter in the population proportion. And then, all right, so that's the mean of the p-hats, population proportion. And then the number we would put here would be the standard error term, whatever that turned out to be. So we'd have to calculate it. But the beauty is that, you know, we're not going to have to do this normal calculation from here on out because we have a calculator function that'll calculate this for us. And then here's the test. If p is less than alpha, we reject the null hypothesis. And If P is greater than alpha, we do not. All right, I know that I'm doing these in kind of segments, and so it's hard to kind of see conceptually the whole process unless you see it from start to finish on a problem. And so I just kind of work through some of the details. The step 3, where all the work does to help you make the decision, where you gather all the evidence, is always going to involve calculating the test statistic. The nice thing about this is that just like the p-value, the calculator will calculate this test statistic for us. And the other thing involved in step 3 is to calculate the p-value, or alternatively, you can use the classical approach and draw this graph. All right, instead of just giving you some more examples of hypothetical sorts of problems, let's work through one from start to finish. All right, so here's our problem, and you can see there's 12 different parts to this, but we only have 5 steps in our test. But this one kind of asks you parts of the 5 steps in the different 12 problems. So I want to go through this one just so you can see from start to finish what it looks like. And I'll point to where the 5 steps of the hypothesis test would be. All right, so here's the National Institute of Mental Health published an article saying that in any 1-year period, 9.5% of American adults suffer from depression or some kind of depressive illness. Now, this result is kind of a stated fact. It's a fact that is known. And if we read the rest of the problem, it says, suppose that in a survey of 200 people in a certain town, 14 of them suffered from depression or depressive illness. And then it says, conduct a hypothesis test to determine if the true proportion of people in that town suffering from depression or depressive illness is lower than the percent in the general adult American population. So this 9.5% is equal to the P0. This is a claim about the population, and the claim down here, it says determine if. They don't actually use the word claim, but what somebody is claiming here is that the percentage in this town that suffer from depression is less than the national average of 9.5%. So they don't think there's a lot of depression going on in their little town. All right, so what we have is N is equal to 200. So they did a survey of 200. So that's our sample size. And they found 14 of them. That's a count. That's an X. That's a number of individuals. So from that one sample of people in that town, we can calculate the sample proportion. It's going to be 14 divided by 200, which is 0.07. So that translates into 7%. And so it looks like the percentage based on this one sample of people in the town suffering from depression might be, since 7% in the town and 9.5% in the general population, it does look like there might be evidence to say that less than 9.5% suffer from depression. Okay, so let's go through these questions. Zoom in on them a little bit. Is this a test of averages? Averages involve numerical data, or is it a test of proportions? Proportions involve qualitative. So that's the first thing. So as soon as you know it's about proportions, then we have a set number of steps that tell us how to do this problem. We're going to be using P, P0, P hat, all proportion variables. State the null and alternative hypothesis. Okay, in this one, the proportion in the town that suffer from depression is the same as the national average. The claim is that the proportion of people in the town that suffer from depression is less than 0.0095, and this is the claim. The 0.095 is describing the whole population, and what they're saying, the claim made here is that the proportion in the town. So we should define the proportion just to keep it straight. The p variable that I'm using here in my null hypothesis is the proportion in the small town that suffer from depression. The p that we're using here is not a statement that the population proportion is 0.095. We know that to be true because of this study up here. But the claim that we're testing is that the small town has a depression rate less than the national average. The small town has a proportion that's less than 0.095. Meets all of our criteria, right? The word claim is next to the claim. We've got the equal to sign in the null hypothesis, greater than, less than, or not equal to sign in the alternative. And we're using an appropriate variable, a population parameter, and not a sample statistic like p hat. We wouldn't use p hat here. Okay, in the chat, right-tailed, left-tailed, two-tailed on this one. Okay, yes, left-tailed. How do you know? The less than sign in the alternative hypothesis. Right there. Less than left, less left. Which symbol represents the random variable? Okay, so what's outcome is based on some random phenomena, and that is the p hat. The p hat is the sample proportion. It's going to change based on the random sample that you select. Not always, and most of the time, it's going to be close to the 0.095, unless this town is really depressed or really non-depressed. The random variable p hat is the sample proportion of residents in the small town that suffer from depression. So it says in words, define what that random variable means. So we've identified the random variable, and then you should always, any variable that you use, you should define what it means. So it's very clear what we're talking about. All right, the next one, number 6, says calculate sigma sub p hat. That is our standard error term for the sample proportion. Make sure to show how you set up the formula. All right, so by formula, this is given to be, it's PQ over N. We do have the N to be 200, and the P and the Q that we're going to use here are the P and the Q that we assume to be true about the population. And so P0 goes in here, and then Q0, and then N down here. So we're going to have 0.095 here, and then we have to take 1 minus 0.095 to get the Q0, and that's 0.905. And that's the standard error term. This is going to help us to construct the sampling distribution, and that number is about 0.0207. All right, so that's number 6. Number 6 says calculate the standard error term. Make sure to show how you set it up. All right, define the following. I think we've already done this one. X was 14, N was 200, and P hat, we take those two numbers and divide them, and we get 0.07. So that's your sample proportion. State the distribution to use in the hypothesis test. That's the Z distribution. We do need to check to make sure N times P0 times Q0 is larger than 10. So if we take 0.095 and multiply that 0.905 and then multiply that by the 200, we get something slightly larger than 10. So therefore, we're using the Z distribution. Okay, next thing. We're going to sketch a graph of the situation. Label the horizontal axis, mark the hypothesized proportion and the sample proportion, shade the area corresponding to the p-value. All right, I'll do what they say. There are other graphs that we can construct here, but the graph they want us to construct here is the one that shows the p-value. So right in the middle is the 0.095, and this is what we assume to be true. We just calculated the standard error to be 0.027, 0.0207. So that would enable us then to construct our sampling distribution. I'm gonna, all right, so this is 0.1157, 0.1364, and 0.1571. Going on the other side, we have 0.0743, 0.0536, and 0.0329. All right, this sampling distribution contains, billions and billions of possible p-hats. When we do a study, we just collect one. All right, so sketch a graph of the situation, got it. Label the horizontal axis, did it. Mark the hypothesized proportion, did it, 0. And the sample proportion. Okay, now the sample proportion is this number right here, p hat. So we're going to place that where it goes on the horizontal scale. Here's 0.05, here's 0.07 and a little bit. So probably 0.07, which is the p hat, would fall right there. Then the p-value that they want us to construct is the probability of getting that sample proportion or something more extreme. And for a one-tailed left test, something more extreme means everything over to the left. And the p-value, we're just going to call it p, which makes it confusing because we have p for the population proportion. This is in a normal situation, a normal setting. So we're going to use normal CDF. I'm not going to do this much, but I wanted to do it on the first couple of problems just because I want you to see how what we're doing right now is linked to what we've done in the past. We want that red area, so you have to specify the horizontal scale boundaries. We're going to go from negative infinity up to the 0.07. And then the mean is the 0.095. And the standard error over here is 0.0207. So that's the p-value. And I'm just going to go ahead and calculate it here so you can see it. So we have entered in everything that we have here. And then when we hit enter, we get 0.1136. I'll just write that. So when it says find the p-value, there it is. 0.1136. At a preconceived alpha, all right, so there's the level of significance. Gave it way down here. A lot of times in these problems, they'll give it right in the beginning of the problem, in the stem of the problem. Okay, so let's use the p-value approach. P in alpha. P is what we just calculated to be 0.1153. Alpha is the 0.10 that they just gave us. And now we need to insert a sign between these two numbers. What's the comparison? What relational symbol do I want to put in here? Less than or greater than? P is 0.1153. Alpha is 0.10. If you want, add a couple more zeros. But you can see here that P is greater than alpha. And if P is greater than alpha, kind of subtly got this in there last time. If P is greater than alpha, we do not reject. So this is how we make the decision based on the p-value. So the decision is do not reject the null hypothesis. Reason, P is greater than alpha. P is greater than alpha. Conclusion, all right, so this is where we, the grid that I gave you the other day. we're going to use that template. So it'll take a while, a little practice to get this down, but we now know that we're not going to reject the null hypothesis. So we're not going to reject that one. So we're not going to be able to show evidence in support of the alternative hypothesis. So we could not reject the null hypothesis, so we could not show support for the alternative. So we could not show support for the claim, in other words. So that's what we're going to write up. There is not enough evidence to support the claim that the percentage of residents in the small town suffer from depression at a rate that is less than the national average, which is 9.5%. So something like that. You got to write a concluding statement that basically spells it out in layman's terms, more or less, you know, what it is that we just found. So someone makes a claim that the percentage that suffer from depression is less than 0.095. We found that, in fact, the sample proportion was 0.007, which is 7%, which is less than 9.5%, but it's not statistically significantly less. This 0.07 could have been just the byproduct of a random sampling variation, and not that the town has a lower depression rate. Okay, now they want you to then answer this question, which says, do you really understand what you just wrote here? Does it appear that the proportion of people in the town with depression or depressive illness is lower than the adult general American population? Why or why not? And the answer is no, since our test suggests not enough evidence to support this, or to support the claim. And so there you have it. This is one complete hypothesis test. Now let me go back through this just to show you, you know, you're not going to have to do all 12 of these steps on every hypothesis test. You just have to do 5. But understanding everything in these 12 items will help you with the 5 steps. So step 1 is to write the hypotheses. Here you have it. Step 1. Step number 2 is to identify the level of significance. Most time that appears at the beginning of the problem. In this case, they gave it a little bit lower in the problem, number 11. Step 2, identify the level of significance. Step 3 is to calculate the test statistic and the p-value. We didn't need to calculate the test statistic here, but if we did, I'll write it in this little space here. Our test statistic is by formula p hat minus mu sub p hat over sigma sub p hat. And we've calculated all these. We've got 0.07 is the p hat right there. The mu sub p is what we assume the population proportion to be, which is the 0.095. And then the standard error term is what we calculated over here, 0.0207. I want to calculate this because where I'm going next is I'm going to take you to the calculator function where they calculate that test statistic and the p-value to go with it. All right. 0.07 minus 0.095, and then we want to divide that by 0.0207. Negative 1.208. And this is the test statistic. Notice we can get the p-value without calculating the test statistic. And you may also notice that this is equal to normal CDF. So if I converted all these numbers to the corresponding z values, we would have negative 10,000, negative infinity. And then this number here would correspond to our test statistic, negative 1.208. And then we'd have the mean and the standard deviation, but we'd be working in the z distribution. So you can check this one too, but you'll find that this one is also 0.1136. But all of this information here is the information in step 3. So step 3. most of what you see on this page that aren't one of the other steps would be the step 3. Then it's very subtle, but down here, the decision, that's step 4. And then the conclusion is step 5. And you can see there's much more on here than just those 5 steps. All right, here's the calculator function. The calculator function we're going to use for section 10.2, this deals with one population proportion, is, well, if you remember for confidence intervals, we use 1 proportion z interval. But now we're doing a hypothesis test. So you want to look for the function 1 prop z test. And there it is on the first page of functions, number 5, 1 prop z test. All right, so here's what they're going to ask you for. The first thing is the P0. So this number P0, oops, I don't want P, is 0.095 in our problem. It's the number in the null hypothesis. The next number that it requests is the x, that was our 14, and the n, which is 120. It doesn't ask for the sample proportion, but the calculator can take these 2 numbers and calculate the sample proportion. So it needs those 2 numbers. Down here is asking you something about the alternative hypothesis. So it has to know if it's going to calculate the p-value if you're dealing with a one-tailed or a two-tailed test, or a one-tailed left test, or a one-tailed right test. And for our test, we had the less than sign, so we're going to select this one here. And that's the middle one. If you do draw, it's going to draw your p-value just like we did here. Let's take a look. All right, so now if we draw, hopefully we'll see this picture. And notice that number right there, that's z, negative 1.2058. Looks very similar to what we have here. Maybe some rounding error. There you can see the p-value, 0.114, p-value, 0.1136. If you select the calculate option instead, it gives you the test statistic, it gives you the p-value, and then reports back the sample proportion. And we can make the decision. So since the calculator gives us the p-value, we're probably not going to calculate it by hand using normal CDF like we did here. We're just going to punch this numbers into the calculator. Now, this problem took us, a half an hour or so. They don't all have to take you a half an hour. So let's go on to our next problem. Grim report. Throughout the country, the proportion of look at that, tells us what the problem's about, a proportion. First year community college students who return for their second year, we call this retention, is 0.52. So just over half of students that attend the community college in 1 year will come back the next year. The other 48% will either drop out or go to a 4-year college or do something else. But this number is the 0.52, and that's our P0. This is something that we know. Suppose a community college institutes new policies geared toward increasing student retention. The first year this policy was in place, there were 2843 first-year students. So this is going to make up our sample size. Of those, 1516 returned. for their second year. Now, if we put those two together, we calculate the sample proportion. And, this is qualitative data. Did the student return? Yes. Or did they not? No. It's not numbers we're looking for. So N is a frequency and sample size, and X is a frequency, the number that returned. So we divide it out, and we come up with a decimal number that we can convert fairly quickly into a percent. I'll round it to 3 decimal places. So the national average is that 52 will return in the second year, and what this college found is it's 53. It looks like the college's retention rate is a little bit higher than the national average of 52%. The question is it significantly higher? Because in order to kind of just throw away the random sampling variation notion, we have to have a sample result that's significantly larger than the national average in order to show evidence for the claim. All right, treat these students as a random sample of all first-year students. Do a statistically significant higher proportion of students. Okay, so here, hidden in here is the claim. And they ask a question, do a statistically significant higher proportion of students return for their second year under this policy after these changes were made at this community college? So their indication is higher. So let's come down here and state the hypotheses. State the claim mathematically. Write the null and alternative hypotheses. Identify which hypothesis is the claim, and define all variables in words. So we're going to say that the proportion is the national average, and the claim is that the proportion of students at this one college is actually larger than 0.52. And that's going to be the claim. So a higher proportion corresponds to P greater than 0.52. And P is equal to the proportion of students retained at, what do they call it? At the community college where policies were changed. I just want to make sure that you understand we're talking about the one college that made the change and not the whole population. So step 1, write the hypotheses. Step 2, level of significance. Alpha is 0.10. So it's a little higher level of significance than we're used to. Okay, identify the sampling distribution. Z distribution. We have N times P0 times Q0 is, well, we have such a huge sample size here that this is going to easily satisfy this criteria. 0.52 and 0.48. Okay, so you can see that if we just multiply N times P times Q, we get this number that's much higher than what we need, which is only 10. So therefore, we're dealing with the normal sampling distribution. It says sketch it, so I'm going to sketch it. So it looks like we're going to be using the classical approach here, as opposed to the p-value approach. Identify the reject and do not reject regions on the graph, find the critical values, and plot them on the graph. Okay. So this is a greater than test. So we're going to have the whole area over here. And this area is alpha, and it's 0.10. So this critical value right here that we would call Z of 0.10, we would get by using the inverse norm function. I have to use 0.90 because I have to use the left area, and that's 1.282. All right, so we are now drawing the normal sampling distribution, and this number right here is 1.282. Here's the critical value, and here's where it is on the graph. Now the critical value corresponds to the alpha. These two are related. There are two other numbers that are related, and that is the p-value, which is another area value, and the sample proportion, which is also going to be, it's going to be somewhere on this scale. So before I add any more to the graph, I will say that if we find any sample proportion that falls out in this range here, where its test statistic is larger than 1.282, then here's where we're going to reject the null hypothesis. So we're not going to accept any old value that's greater than our 0.52. It has to be significantly greater. And then any sample proportion that leads us to a value over here, our decision is going to be do not reject the null hypothesis. Okay, so find the standardized test statistic. That's the z sub 0 given by this formula. Now, normally I wouldn't even bother with this formula because the calculator function will give us this value. But I'll calculate it this time. We have 0.533. Okay, remember our sample proportion that we calculated up here? Here it is, 0.533. Minus what we assume to be true about the population. That is, its population proportion is 0.52. And then we have to divide by the standard error term. And remember that the standard error term is the square root of P0 Q0 over N. So if we're going to use this one, it would be 0.52. And then 1 minus 0.52 is 0.48. And then we have to divide by the sample size in this problem, which is the 2843. So this is going to lead us to a very, very small standard error term. I'll evaluate it here. I'll call it 0.0094. All right, then I'm going to evaluate this, 0.533 minus 0.52 divided by 0.0094, and we get 1.38. Okay, now we're almost ready. We're going to plot this value on our horizontal scale. This is the test statistic. There's two z values that you want to plot on the horizontal scale. One of them is the critical value that we've been calculating for several weeks now, maybe in a different context, but we've actually calculated this number several times. And then we're going to plot this number. And this number is our test statistic, or standardized test statistic. We're also going to plot this value on our horizontal scale. Here is 0, and here is 1.282, and 1.83 then would be right about here, 1.38. It's just over this line in the sand, but it puts us into the reject region. So when we plot this number, it puts us into this critical region here in the reject region. So our decision is reject the null hypothesis. Give the reason. The test statistic, and in this case, it's z sub 0 that we just calculated. The test statistic falls in the reject region, falls here. In this case, our sample proportion led us to a number, what we call statistically significantly larger than 0.52, even though it was only 0.533, 52% versus 53%. Not a big change indeed. All right, and then the last step is interpret the results in context. So since we rejected the null hypothesis, the way that I will indicate that is I'll come up here and I'll say, oh, we reject this. So therefore, there's evidence in support of the other hypothesis. There's evidence in support of the alternative hypothesis. So I'm going to say that there's evidence to support the alternative, which happens to be the claim, that the proportion is larger than 0.52. So just provide some more details, but other than that, we're going to say there is evidence to support the claim that the proportion of retained students after the new policies were put in place is larger than what it was before those procedures were put in place, 0.52. So this last part here basically says there's evidence to support the claim, and then you just come up here and say, well, what was the claim? Well, the claim was that P was greater than 0.52. Well, what does that mean? Well, we defined P over here, so the proportion of students retained at the community college where policies were changed is greater than 0.52. So you can just kind of state the alternative hypothesis in words there. I think this one more parallels the 5 steps. So for example, part A, you have the step 1, write the hypotheses. We don't give a kind of a part B for this one here, but I suppose I could ask you what's the level of significance, and then you just have to look at it there, but not actually one of these problems. But we do use it down here. Step 3 would be this one, where we gather the evidence, calculate the test statistic. This one here as well. And then to make the decision, that's step 4, part D. And then to state the conclusion, that's step 5. So those are the 5 steps that I'll kind of go through for each of these. I also, for this one, would like to give you another example of how you use the calculator function. So one prop is Z test. Go ahead and give me these numbers. I want to see if you're following along. It's going to ask you for P0. What's that number? It's going to ask you for X and N. And then it's going to ask you something about the alternative hypothesis. Is it not equal to, less than, or greater than? See, the numbers that you have to give the calculator are the numbers that would enable it to calculate the test statistic and the p-value. So here's the test statistic. We need p hat. Well, we can find p hat. If you give it X and N, the calculator can calculate p hat. Minus p0, well, that's why you have to enter in the p0. Divided by the standard error term, but the standard error term involves P0, Q0, and N. You've already got N, you've already got P0, you could easily calculate Q0. So if we give just these 3 pieces of information, it'll give the calculator all the numbers that it needs to calculate the test statistic. And in fact, the output will be the test statistic, but it'll also give you the p-value. What's the p-value here? Okay, good. Yep. 0.52, and those other numbers are kind of up here, X and N, 15, 16, and 28, 43, and the calculator will put them together and give you the 0.53 that we calculated earlier. And then this is our P0 value. And then what you see is greater than P0. So the alternative hypothesis is greater than P0. So that's why we select that one. I should probably make sure that these are in the right area. All right, and then the output will be the test statistic and the p-value. Now you don't need to do this because we just calculated these 2 numbers, right? You've got the test statistic, 1.38, and I guess I didn't calculate the p-value here. But it would be the area, I'm going to draw it here, from our test statistic over. So you can see that the red area here is less than the whole black area. So P is less than alpha, which would lead us to reject the null hypothesis as well. All right, stat. .412. And boy, we got something off a little bit, right? Probably some rounding error there. And the p-value is 0.078. And the p-value 0.078 is less than alpha, which is 0.10 in this case, not 0.05. So and there's our p-hat, rounded to more decimal places than we have, 0.533 sample size. And then z, 1.4129. Okay, you can see I have some rounding error here, but it's close. When you're in doubt, use the calculator number instead of this rounded version. P is 0.0788. Alpha is 0.10. P as a number is less than alpha. And if P is less than alpha, we reject the null hypothesis. So we didn't need to do this because we already made the decision using the classical approach. Right down here in part D, we noticed that the test statistic fell in the critical region, so we're going to reject the null hypothesis.